Welcome to lecture number 14 on measure and integration. Today, we will start looking at functions on measurable spaces. So, these are called measurable functions. To start with, we will assume that we have a measurable space x S. So, x is a set, S is a sigma algebra of subsets of the set x, and we have a function f defined on x taking extended real values. So, R star denotes the set extended real line, that is a set of all real numbers together with plus infinity and minus infinity and with the possible operations that we had defined earlier. So, we will be looking at functions which are extended real valued defined on the set x. To start with, we want to prove the following, namely for this function f, the following statements are equivalent: inverse image of the interval open interval c closed at infinity. If we take the inverse image of any such interval, then that belongs to the sigma algebra S. We will show that this is equivalent to saying that the inverse image of the closed interval c to infinity belongs to S for every c the real number, and also this is equivalent to saying that the inverse image of the interval minus infinity to c, minus infinity closed, c open, also belongs to the sigma algebra S, and then we will show that this is also equivalent to saying that the inverse images of all the intervals of the type minus infinity to c, c closed belongs to S for every c belonging to R. So, we will show that these four are equivalent to each other, and also these are all equivalent to the following, namely the points f inverse of plus infinity and the set f inverse of minus infinity, along with f inverse of every set E, a Borel set in R, they belong to S. So, we will show that for a function f defined on x taking extended real values, extended real numbers as the values, these 5 conditions are equivalent. So, methodology is going to be, we will prove 1 is equivalent to 2, 2 is equivalent to 3, 3 is equivalent to 4, and any one of them is equivalent to 5. So, let us start proving these properties. So, first property is, so we are given that f inverse of c to plus infinity belongs to S for every c belonging to R, and we want to prove the same property for f inverse of, keep in mind what is f inverse. This is the f inverse of c plus infinity is the set of all points x belonging to x, so that f x belongs to c to plus infinity. So, this is a set of all points x in the domain which are mapped into the interval c to infinity. F inverse does not mean that the function is invertible or anything, just this is a symbol used, it is a pullback of the points which go into this c to plus infinity. So, we want to look at f inverse of closed interval c to plus infinity, and we want to show that this belongs to S. So, to show that, let us observe the simple set theoretic equality, namely the closed interval c to plus infinity can be written as intersection of, look at the open interval c to c minus 1 by n to plus infinity, and look at the intersection of all these intervals. So, keep in mind here is c and here is c minus 1 over n. So, if you take this open interval, so this open interval c minus 1 by n to plus infinity includes this closed interval c to infinity for every n. So, intersection also will include it, and actually this is equal, because given any point which is slightly bigger than c can be excluded by taking n sufficiently large. So, c minus 1 over n converges to c, that is the basic idea. So, this is a simple identity about intervals which should be easy to prove. So, and then this implies that the f inverse of c to plus infinity is equal to f inverse of intersection n equal to 1 to infinity of c minus 1 over n to plus infinity. And here is another simple observation, that the inverse images of intersections are same as intersection of the inverse images. So, this is equal to f inverse of c minus 1 over n to plus infinity closed. And we are given that whenever the interval is of the type c to plus infinity, C open, inverse image is in S. So, each one of these sets belongs to S. S is a sigma algebra. So, intersection belongs to S. So, this belongs to S. So, basically what we have done is the closed interval C to plus infinity is written as the intersection of open intervals C minus 1 over n to plus infinity, and observing that the inverse images of intersections are intersections of inverse images, we get that f inverse of the closed interval C to plus infinity belongs to S. So, this implies, so we have proved 1 implies 2. Let us show that 2 also implies 1. So, what is the statement 2? Statement 2 says f inverse of the closed interval C to plus infinity belongs to S for every C belonging to R. So, that is the statement 2. So, we want to now prove the same thing for open intervals. So, the idea is the open interval C to plus infinity can be expressed as union of the closed intervals C plus 1 by n to plus infinity, n equal to 1 to infinity, and that is quite easy to verify. The interval C plus 1 by n is to infinity is inside the interval C to plus infinity. So, this union is inside it, and conversely is easy to check that because C plus 1 over n goes to C, this is actually equal to C to infinity. So, now once again observing that the inverse image of C to plus infinity is equal to f inverse of the union n equal to 1 to infinity C plus 1 over n to plus infinity, and once again a simple observation that the inverse images of union is union of the inverse images. So, that gives us that this is f inverse of C plus 1 over n to plus infinity, and we are given that each one of them belongs to S, and this is a union of union of sets in S. S is a sigma algebra. So, implies that this set also f inverse of C to plus infinity also belongs to S. So, hence we have shown that 2 implies 1. So, 1 implies 2 and 2 implies 1. So, thus we have shown that the statement 1 implies statement 2 and the statement 2 implies 1. And if you see the proofs carefully, in both of them we have just tried to represent a closed interval as a intersection of open intervals, and also on the 2 implies 1 we have tried to use the fact that you can represent an open interval as a union of closed intervals. Similar facts are used in proving the remaining statements. So, let us just prove the remaining statements, namely 2 implies 3. So, let us prove 2 implies 3. So, the statement 2 is regarding closed intervals. So, we are given that f inverse of this belongs to S for every C belonging to R. So, that is the statement 2 which is given, and we want to show that f inverse of minus infinity to C open belongs to S for every C belonging to R. And if you look carefully, this interval and this interval are related with each other, they are namely complements of each other. So, the given statement implies that this, because this belongs to S, so its complement. So, x minus f inverse of C to plus infinity also belongs to S, and this set, the complement of this is nothing but. So, here is a small observation that the complement of the inverse image is nothing but the inverse image of the complement. So, this set is equal to f inverse of R star minus C to plus infinity, and that is equal to f inverse of minus infinity to C open, because here C is closed. So, this also belongs to S, because S is a sigma algebra. So, if a set belongs, its complement belongs. So, this belongs to S, and see, all these statements are reversible. If this belongs, then its complement belongs. So, these are all if and only if statements. So, 2 implies 3 is obvious by taking complements. Let us prove 3 implies 4. So, the statement 3 implies, so what is given to us is f inverse of C to f inverse of minus infinity to C open, that belongs to S for every C belonging to R. And from here we want to conclude this closed interval. So, once again note that the closed interval to C is equal to. So, let us we want to include the point C inside. So, it is nothing but look at minus infinity to C plus 1 over n, the open interval. So, here is C and here is C plus 1 over n. So, this interval, the closed interval, is already inside C plus 1 over n for every n. So, if I take the intersection of all this, so that will give us the closed interval minus infinity to C. So, it is similar to the earlier argument. So, this implies that f inverse of minus infinity to C, which is equal to, so f inverse of the intersection, that is intersection of the inverse image, is f inverse of minus infinity to C plus 1 over n open, and each one of them belongs to S. So, this belongs to S. So, 3 implies 4. So, if f inverse of minus infinity to C open belongs, then f inverse of minus infinity to C close also belongs. So, 3 implies 4, and let us prove the converse statement, namely 4 implies 1. So, if we are given f inverse of minus infinity to C closed belong to S for every C belonging to R, and we want to look at f inverse of the open interval C. So, once again it is similar situation, that is minus infinity to C, it is here, and we want to look at the open interval. So, let us look at the union of intervals minus infinity to C minus 1 over n equal to 1 to infinity. So, they are all, here is C minus 1 over n. So, these are all inside it, closed interval. So, the unions will give us this open interval. So, once again taking the inverse image is minus infinity to C is equal to f inverse of the union n equal to 1 to infinity, and f inverse of the union is union of the inverse images. So, that gives us minus infinity to C minus 1 over n, and all of them, each one of them is given to be inside S. So, that implies that this belongs to S. So, 4 implies 3, also true. So, what we have shown till now is that all the first 4 statements are equivalent to each other. So, first statement was about intervals of the type minus infinity to C to infinity open, then the next one was C closed, and then next was minus infinity to C. So, all inverse images of all these types of intervals are inside R, inside S, all these statements are equivalent to each other. Now, let us prove that this implies that f inverse of plus infinity and f inverse of minus infinity and f inverse of every Borel set is inside S. So, let us assume any one of 1 to 4. So, assume any one of the statements 1 to 4, hence all. because they are all equivalent. So, we know that f inverse of a interval belongs to S whenever for every interval I, which looks like either C 2 plus infinity or looks like closed C 2 plus infinity, or it looks like minus infinity to C open or minus infinity to C closed. So, for these four type of intervals, the first any one of the first four statements implies they belong to S. Now, look at any other interval. Supposing I is a open interval a to b, then we can write this open interval a to b as minus infinity to b open interval intersection with minus infinity to b intersection with the open interval a to plus infinity. And we know that inverse image of this interval belongs to the sigma algebra, inverse image of this belongs to the sigma algebra. So, that will give us that the inverse image of a b is equal to f inverse of minus infinity to b intersection f inverse of a to plus infinity, and both belongs to the sigma algebra. So, this will belong to the sigma algebra S. So, what I am trying to say is that any one of the statements 1 to 4 imply that inverse image of every open interval also belongs. And similarly, we can take actually a closed interval also. For example, a closed interval a b can be written as minus infinity to b intersection a to plus infinity, and similar argument will imply that in f inverse of this interval also belongs to S. So, if we assume any one of these statements 1 to 4, then that imply that f inverse of every interval belong to S for every interval. Now, recall that in the real line, any open set, say open set in R, is a countable union of open intervals. So, in R, say open set is U, then U can be written as union of I j's, j equal to 1 to infinity, I j's open. Actually, we can write it as a disjoint union of open intervals also. It's countable disjoint union of open intervals. So, f inverse of U will be equal to f inverse of union disjoint union of I j's, and which is same as union of f inverse of I j's, j equal to 1 to infinity. Actually, disjoint is not needed, but anyway this is okay. So, and f inverse of every open interval belongs to S. So, this belongs to S. So, if we assume any one of the four conditions, then that implies that f inverse of every open set is in the sigma algebra. So, now this here is a sigma algebra technique. So, consider the class A of all sets belonging to S, all sets belonging all subsets in B R such that f inverse of E belongs to S. Then just know what we showed, the open sets are inside A, and it is easy to check that A is a sigma algebra and A is a sigma algebra. So, let us check that A is a sigma algebra. So, why A is a sigma algebra? So, clearly empty set and the whole space R belong to A, right, because X and the empty set belong to S. Secondly, let us observe that if a set E belongs to A, that it means that f inverse of E belongs to S, and that implies that f inverse of E complement belongs to S, because S is a sigma algebra, and that is same as f inverse of E complement belong to S. So, implies E complement belongs to A. So, A is closed under complements, and finally, if E n's belong to A, that implies and f inverse of E n belong to S. So, implies union of f inverse of E n's also belong to S, because S is a sigma algebra, and hence that implies that union of inverse images is inverse image of the union. So, union E n also belong to S. So, implies union E n's belong to A. So, we have proved verified that A is a sigma algebra. So, this is a sigma algebra including open sets. So, it must include the Borel sigma algebra inside, but is already a subclass of Borel sets. So, A is equal to the class of Borel sets. That means, if we assume any one of those first 4 conditions in the statements that we just now stated, then that implies the statement that f inverse image of every Borel set is in the sigma algebra S. Let us verify that the inverse images of the points plus infinity and minus infinity are also. So, note that plus infinity can be written as intersection of n to plus infinity, n equal to 1 to infinity, right. So, f inverse of plus infinity is equal to intersection n equal to 1 to infinity f inverse of n to plus infinity. F inverse of this is equal to f inverse of the right hand side. Right hand side is a intersection. So, it is intersection of the inverse images, and each one is an interval. So, that f inverse image of each one of the intervals belong to S. So, intersection belongs to S. So, this belongs to S, and a similar argument for minus infinity will imply, because minus infinity can be written as intersection of n equal to minus and 1 to infinity of minus infinity to minus n. So, inverse image of this will be intersection of inverse images and will imply that f inverse of minus infinity belongs to S. So, we have shown that if you assume any one of those 4 conditions stated above, then that implies that the inverse image of the point plus infinity and inverse image of every Borel set belong to the sigma algebra S. The converse statement is obvious, because every interval is a Borel set. So, saying that statement 5 implies any one of the statements 4 above is obvious, because every interval is a Borel set, that is a special case. So, we have proved this theorem, namely for a function f defined on a set X taking non extended real valued functions, all these 5 conditions are equivalent to each other, and if you assume any one of them, then other remaining will also hold. So, a function which satisfies any one of these conditions is called a measurable function. So, a measurable function on X taking extended real valued is a function which satisfies any one of those 5 conditions as stated here. So, these are going to be important class of functions for us to deal with. Let us look at some examples. The first example is that of what is called the indicator function of a set. So, let us look at what is called the indicator function of a set X. So, let us take X any set and A subset of X. So, we define a function called the chi of A. This is the Greek letter chi. So, lower suffix a function on X taking 2 values 0 or 1. So, this is called the characteristic function or the indicator function. So, this function takes the value at a point X, the value is 0 if X does not belong to A, and at the point A the value is 1 if X belongs to A. So, here is the set X, here is the set A. So, on A it gives the value 1, and on outside A it gives the value 0. So, it is a 2 valued function. It indicates, so the points where it takes the value 1 is exactly the points in the set A. So, this is called the characteristic function. So, characteristic function or the indicator function of the set A. So, this is called the indicator function of the set A, and the claim is, so we want to look at, so X is a set, S is a sigma algebra, and we have got the indicator function A of the set A on X taking values, of course, only 2 values. So, we can consider it as a function in taking extended real values. So, we want to know, is it measurable. So, suppose the indicator function of A is measurable. So, that implies, if I look at chi A inverse of the singleton point 1, that belongs to S. But what is that value? So, what are the points where it takes a value 1? That is precisely A. So, that is the set A. So, A belongs to S. So, if the indicator function is measurable, then we get A belongs to S. Conversely, if A belongs to S, we claim that chi of A is measurable. So, for that, look at chi A inverse of any interval I. So, what is that going to be? The inverse image of an interval is going to be equal to empty set if 0 or 1 does not belong to the interval I, because then there is no point which goes to the interval, and it is equal to A if 0 does not belong to I and 1 belongs to I. And similarly, it is A complement if 0 belongs to I and if 0 belongs to I and 1 does not belong to I, and is equal to X if both 0 and 1 belong to I. So, in either case, either it is empty set or it is a set A or A complement or X, and all of these are elements of the sigma algebra S. So, inverse images of every interval is in S. So, hence the indicator function is a measurable function. So, what we have shown is that the indicator function is measurable. So, this indicator function, which is defined as 1 if x belongs to A and 0 if x does not belong to A. So, the characteristic function is measurable if and only if the set A belongs to S. So, this is the simplest example of a measurable function. Let us consider a linear combination of the indicator functions. Suppose S is a function defined on x, say that S of x is equal to A I times the indicator function of a set A I evaluated at x I equal to 1 to n. So, look at sets A 1, A 2, A n, subsets of x, look at their indicator functions and take a linear combination of them A I times the indicator function of A I. Such a function is called a simple function on x. Such a function is called a simple function on x.